Hi, I'm Dustin Frost. You may remember me from my previous instructional video on how to fix your dishwasher. This time, I want to help you fix your conception of the universe, or all the very basic fundamental parts of it and how it works together. In a way, uniting the very large things with the very small things, basically all the things and how they work together. And that might sound like kind of a grandiose claim, especially coming from a guy like me. And it is, you know, I'm not going to lie, it does to me seem like a big idea, and an important one, which is kind of why I wanted to show it. But in another way, it's also not a lot different than the other video I posted, which was just, I broke my dishwasher by accident. The fix seemed like it had to be really simple, but everything else, trying to find like how to, repair it seemed really hard. And then I figured it out and like, well, I'm going to share this. I think this is basically the same thing. I started with a really small idea, basically trying to understand if gravity had like a left or right-handed rule like electronics. Left or right-handed, I guess, depending on if you're a whole flow or electron flow guy, but don't worry about that. Uh, and then it occurred to me, what Einstein had always said is that mass and energy are the same thing. Not just that they relate to each other, by this formula, but they are essentially the same thing. Uh, and so, following that idea, I had a lot of weird ideas, or at least so my friends thought, or the few that were kind enough to listen to me. But even though those ideas were weird, I kept following them, trying to unweird them to make them more logical and concise. Eventually, trying to use mathematical language to describe the relationship. And the more I worked at it, the more I started to understand, this thing. So, and then eventually, that light bulb kind of like went off, and it kind of all fit together. And after that point, I couldn't unsee it. So I'm hoping that it'll be that way for you guys and girls. Uh, so let me just go ahead and get into it. Uh, Essentially, first we're going to start off talking about dimensions. What is a dimension? Uh, and at the heart of it, a dimension is just a quality or an aspect of something. Uh, if you look at the ancient Greek, root of the word, you have die meaning two, and mentia meaning measurement. So two measurements, or let's just say more than one measurement or multiple measurements. And the idea is that this one aspect, can be used to compare to other aspects. So let's say if you look at your foot and you see it is so long, you can go and measure everything else with your foot. And as long as your foot stays the same size, and as long as everything you measure with your foot stays the same size, then you can use your foot as a measurement or a foot dimension of, whatever it is you're measuring. And basically all dimensions, work like that, or at least they're going to in this discussion. So yeah, so a dimension is a quality, an aspect that you can measure by repeatedly and consistently. And so anything can be a dimension. Like like a foot can be a dimension. This whiteboard could be a dimension. A wavelength of light, a light year. Anything you care to name can be a dimension. But yet at the same time, every dimension is also made up of other dimensions. So the foot example, let's use the standard foot, not my foot. Or you can use your foot if you want. But sorry, I'm a dork. But every dimension is made up of other dimensions. And you could, in some ways, say smaller ones, but that's not entirely accurate. I don't want to use that definition, but let's just go with it for now. So a foot, you can divide a foot into inches, 12 of them usually, and you can divide the inches into quarter inches and so forth, or you could use a similar but different measurement of meters and centimeters, and you have these nice mathematical progressions of measurements. Uh, and so all dimensions are like that. But what we're going to do is look at the basic overriding fundamental dimensions of reality, the universe, or more specifically this conversation, causality, which is, you know, how everything fits together, affects everything else, basically everything being a part of everything else, or at least in the broader understanding of the system of everything else. We are all part of the universe. Uh, yeah, you know, we're all stardust and things like that. But, you know, we can't be outside of the universe. We have to be inside of the universe. And there can only be, in that sense, one universe. You know, one thing that contains everything, or everything making up one thing. It works both ways. So let's let's go ahead and before I get more tongue-tied and start, and hopefully it'll make sense. Uh, I promise you, I'm not going to get into any woo-woo stuff. I'm not going to have any, I hope, I think, undeclared, untestable, unverifiable aspects of this. In fact, my contention is that the universe is basically, essentially understandable. That we could look out, well, we do look out. We look out at the universe every day and we understand what we're looking out at. We don't, you know, look at a camera and say, whoa, what is this camera? You know, or how do I see this camera? We just do. And in that sense, our knowledge of the universe works perfectly fine. But back in the beginning, I did say our conception of the universe, and that part's a bit trickier. That part we've had to build up over, you know, a few hundred years now. Like, how do, you know, what does all this stuff do? You know, how does it work together? What does it mean? You know, and we've been building on this conception over time, but obviously our conception is limited. You know, there are aspects of the universe that we don't quite understand. Particularly this video, dark matter and dark energy, what gravity is, what space is, like what makes everything up. Uh, and I'm going to tell you off the bat that everything makes everything up. Everything works together to make everything. Uh, there are no monads, which is, you know, a fundamental, you know, inseparable component of something would be a monad. And there aren't any, at least not that I've seen. Uh, so it's kind of turtles all the way down in a sense, but trust me, it'll make sense in a second. So the first thing I want to talk about after this idea of dimensions is dualities. So if you take a very fundamental dimension like a number line, uh, you have your counting numbers, right? You have 1, 2, 3, 4, yada yada, on into infinity, or at least as far as you care to count. You know, and this is, and you can use this number line if, let's say, it was a physical thing, just like you would a ruler or a yardstick. Uh, but there's something kind of missing here, and you know that is the negative numbers. Now, I should say before I get to the second part here, you know, this is what we consider the real side. You know, we can actually look at something and see one of something, or you know, we can look and see two, but we can't look and see zero. We can't look, you know, at least not without comparing to something that should be there, right? You can't just on its own basis see a zero or see a -1 or, you know, any of these kind of imaginary or comparative type constructs. But we do have those imaginary comparative type concepts. We have the imaginary numbers. We have -1, -2, -3, on and on, up to as far as you care to count, or can count, or have time to count. And anyway, and then in between these guys, you have the zero, the balance of two opposing things, the have and the have not, the be not. The one and the one not make this, you know, this zero balance point. And it's almost like a mirror is drawn between, and each side is a reflection. You know, and from our side of the mirror, you know, this would be, you know, us, the real world, and this would be the reflected world. Although, if, you know, maybe in a Lewis Carroll type sense, maybe you're on this side of the mirror and all the positive numbers are imaginary. Who knows? But you'd probably still call them positive numbers and call these the negative numbers. Just like if you're looking at electric potential or anything at all like that, it's always this thing compared to that. It's about perspective of where you are. Speaking of perspective of where you are, uh, sorry about that. Here we go. So if you have an infinite number line, you know, infinitely negative and infinitely positive on one side, and I'm going to use the word infinite a lot, but I'm going to say from the start, you're never going to find infinity. In some ways, infinity is just saying you're never going to get to the end of it. It's there as much as you care to look. And the universe seems to tell us that, right? We can investigate the universe as much as we want, and the only limit we've found is the limit of our own ability, of our telescopes, of our microscopes, of our scientific and visual and auditory and entire sensual acumen determines what we can find, not this, there's no hand stopping us out there and saying, no, you shall not pass, and hopefully no Balrogs either. But if you, sorry, if you have an infinite number line, and this side is, positively towards infinity, and this side is negatively towards infinity, then you could essentially put your finger or a marker down anywhere on this line, and you're still going to have infinity to the left and infinity to the right. Here I am stuck in the middle with you. But that was horrible. I apologize. I don't know where it came from. So basically, anywhere on this line from the perspective of itself is just the same as if it was right here, but balanced right between the two. Zero from your perspective is always going to be zero because there's always going to be infinity that way, and there's always going to be infinity that way. Or at least you can't see the end of it, whatever it is. And that's going to be important here in a bit. So here we have this idea of duality with a real part and an imaginary part. And we see these dualities a lot. We see them, in the numbers, and we see them in our day-to-day life. A lot of ways we're familiar with are like two sides of a coin, or there is no good without evil, or these opposing realities that kind of like make a broader judgment of how the system works. So same thing with negative and positive numbers. But beyond numbers, there are some dualities that we've become aware of over the last couple hundred years, especially over the last 100 or so. And speaking of the last 100 or so, the great Albert Einstein gave us a very important one, which is mass. Well, you know what? I'm getting ahead of myself. But mass and energy is going to be our first duality. But before we get to that, you know what? We're going to talk about a different duality. So we're going to talk about describing the entire universe and describing its dimensions or its characteristics. And so, like I said, anything can be a dimension, and you can plot it on a graph. If you were doing a study on the number of independent voters in each state, then you could do, this side for number of voters, and this side for states. You could have Alabama, Alaska, Arizona, et cetera, and so forth. And you could like mark here for this number of independent voters, here, and you could make a graph, like that of these two dimensions. But in this case, there are a lot of different ways you could break down the demographics of, our country, any country of the world. So you have more than two axes. But when we're dealing with dualities, like let's say, base 10 numbers, as we were using before, you can have negative numbers and positive numbers, but to the best of my knowledge, you can't have negapositive numbers, or there's a third category of number that's neither negative nor positive. You have this very strict duality. So, as I said earlier, mass and energy is one of those dualities, but I'll get back to it. But first, we're just going to, we're going to make a graph, basically, as we go along. And it's going to work mostly like your Cartesian coordinate graph, x, y, and z. But we're going to start with just this circle right here, this little tiny circle. And we're going to say this circle represents everything. All right, there's everything. There it is. I've explained everything to you. Hope you guys enjoyed the video. Kidding. So this circle is everything, but just everything like that's not going to do us a lot of good. You know, we need to break it down. So we're going to expand everything. You know, we're going to have like an outer limit of everything. And I apologize in advance for not being able to draw straight circles or lines. So here is everything. Here is the universe, not to scale. Old Mr. Hobson joke. So now that we have our basics here, you know, we have this entire edge of this circle here is going to represent infinity on any side. In fact, you can, instead of thinking of this as a circle, we're going to do 3 dimensions. In fact, we're going to do a bit more than 3 dimensions, but it's not going to be crazy weird dimensions like you're not familiar with. They're dimensions that you know of but don't know you know of. So consider this more like a sphere and a sphere plus, a supersphere. That's probably a thing, like a hypercube, a hypersphere. But anyway, here is the circle of the universe. Here's everything out here, and in the very center there is nothing. And you can never actually find nothing in the universe. At least we haven't found it yet. And you're like, oh no, I've seen plenty of nothing. I'm like, no, you haven't, because you can always look closer. You could look closer and then you'll see, you know, at least on this planet, you'll see air molecules, and you look closer and you'll see atoms, and you look closer at those and you'll see quarks, you know, and gluons and all that kind of good stuff. So you'll never actually find nothing, no matter how far you look, either in any direction that you care to travel, or in this idea of scale of bigger, you know, you look out farther and farther the universe. And so far, James Webb Space Telescope has not found an edge of the observable universe. And I'll go ahead here and lay a wager of $100 to anybody who wants to put it up that we're not going to find ever the edge of the observable universe. It's going to appear, it is going to just keep going on as far as we can look, because everything does, right? Numbers do. You can count as far as you care to count. You know, we haven't found the end of pi yet, all that kind of stuff. So, but just for the sake of it, we're going to say there's nothing in the middle and everything on the outside. But you also notice that that nothing right there was originally our entire universe, and we just kind of stretched it out and left nothing right there in the middle. And we, you know, introduced this idea of scale here. So let's keep going before I beat that into the ground anymore. So as I mentioned earlier, our first duality of, you know, and just like if we were doing like a Cartesian graph, we would need a duality of, you know, positive, you know, positive, negative, 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 positive. You know, we would have dualities already, and we're going to need these dualities to describe our causal universe. So, all right, let's finally get it on the board and keep it there. So here's mass, and that is our real part of the line, because you can look out and see mass. We don't, you know, you can say that, you know, this whiteboard has an equivalent amount of energy to its mass, but we don't actually see the energy. Even when we see things like light, lightning, you know, you can't see heat, right? You can see the things moving, you know, under the effect of heat, you know, the molecules vibrating, but you can't actually see the energy. So we're going to call energy our imaginary part. And we have energy. And the arrows here, just because, you know, this is going towards infinity and this is going towards 0, because you can keep going farther and farther to 0, either with mass or with energy. You know, you'll never run out. Like the whole Zeno's paradox, you just keep dividing it, you're going to be able to keep dividing it. So mass and energy, and they, you know, form the greater axis of what we call matter. So it's one thing, it's matter, but it's divided into two things, mass and energy. You know, I was talking about the duality earlier. I mean, you could graph it like this. You could have mass on this side, energy on this side. And let's say you have this much mass and this much energy, and you could draw a line here. You know, this side plus this side is, you know, going to be, you know, the whole Pythagorean theorem. A squared plus b squared equals c squared. So we're going to get this thing here representing the total amount of matter in this, you know, energy and mass. And we're not going to find anything else in matter that's not energy or mass. So there's a duality. Okay. And then, like I said, this is the imaginary part. This is the real part. Get rid of that for now. All right, so we have one axis, and it's useful, especially because, you know, if we look at like this kind of mirror relationship across the center. Sorry, quick aside. There aren't going to be any negatives. You know, like if we were using a Cartesian graph, we would consider this side negative. Don't consider this side negative. You can consider it a inversion or reflection of the other side, but that doesn't mean it's negative, at least not to the best of my ability to tell. I could be wrong, but anyway. But we also know that mass and energy, you know, relate to each other at the rate of c squared. So you have this side is c and this side is c. You know, and just like if you were walking away from your image in a mirror, you know, your image in the mirror is going to walk away from you, and, you know, your distance is going to increase at the rate of whatever your rate of movement is squared, because both sides are going to do it. I move this much, my reflection moves this much, the movement is this movement squared. And now I'm dancing on camera. Don't get used to it. Okay. Cool, but we need more. So let's put some more stuff up there. And I'm sure most of you probably know where I'm going to go next, but let's go ahead and do it anyway. So our next axis is going to be blue, space, the final frontier. All right, so you have one axis of space and this other axis, you know, this other side of it that we know of time. Space-time. So we have the matter axis and we have the space-time axis. Now, I'm pretty sure that these also are going to have the same value of c comparatively. Somebody else is going to have to do the math on that or verify it. I haven't found anything to support this, at least not really, maybe. Sometimes some things I've looked at have kind of seemed like it might support it. But essentially, we know that space and time are the same thing. We call it space-time, when we're not quite sure what space is, we're not quite sure what time is, but we know they're really closely linked, because in fact they're different axes of the same thing. And we see this in our day-to-day life too. You know, if you have to drive the next city over, and that city is 100 miles away, you know, and your rate of speed is a certain miles per hour, kilometers per hour, you know, what have you, then it's going to take you like this X many, you know, let's say you're driving 100 miles an hour down the highway. It's going to take you 1 hour to get there. So it's going to take 1 hour, and it's 1 hour away. So there's kind of like already you can see this reciprocal relationship of, you know, time forward, space backwards, or at least, you know, a kind of inversion of it. You know, once you've traveled the distance, you've taken away the distance, but you've added time, and that's important. All right, so we have space-time as another axis. And, you know, you see here now we have our typical XY, you know, Cartesian coordinate graph. We have two axes, matter and space-time. And for the most part, that tends to describe everything that we see, you know, in the classical sense, right? We look out and we see a bunch of mass separated by a bunch of space, and from it we infer a bunch of time, or the passage of time, and we can infer energy from how the mass behaves in space. So two dimensions satisfies the basics of three-dimensional reality. And I think this is strongly connected to the holographic principle, but that's a bit beyond my field of expertise, as is the whole thing, but definitely making much of a projection beyond that little guess. All right, so we have two axes, and we can plot, coordinates here. We can have this much mass in space. We can have this much mass over time. All right, but obviously that's not sufficient enough to explain our reality. And when I say sufficient enough to explain our reality, I am saying that this does kind of represent our perspective on reality. In this case, we have two dimensions, but this is going to mirror everything that we see in the universe. So let's just go ahead and get our next axis in here so we can have three-dimensional causal reality. So we're going to add one guy here in the real realm and one guy here in the imaginary realm. And that's imaginary as in that, not as in like the land of Hanali. Whoa, where did that reference come from? And so, and each of these, this axis is perpendicular to this one, and this one is perpendicular to the other two. So just like your X, Y, and Z graph, I'm just drawing a diagonal here to artificially represent three dimensions. And you're saying, okay, that's great, Dustin. What's the darn axis? Well, it's actually one we've already introduced. I snuck it in and didn't tell you about it until just now. So that axis, remember when we had the little tiny dot representing the universe? We decided to blow it up and stretch it out to make two different sides of it, the zero side and the infinity side, so we could fit everything in between those two poles. Well, that is this axis, and that is the axis of scale. Scale up or increasing, and scale down or decreasing. Bigger, smaller, outside, inside, all of that kind of stuff. So now we have three dimensions. We have just like we do, with our real world. But like right now, you're probably scoffing a little bit for good reason, especially because, like I said, we've already had scale here the whole time. It's just we're only recognizing it right now. But it is this idea of scale here that gives this idea of scale here and quite probably here. So the whole C actually comes from this axis of scale. Without scale, there would be no C. And perhaps without C, there would be no scale. But we just call it something different. I don't know. So here's three dimensions. But as I said, we already have this, so we don't really have, it's kind of a pseudo three dimensions. So just to kind of get rid of that little friction there, I'm going to put in another dimension. And on one hand, it's a dirty bit of cheating, but on the other hand, it's absolutely necessary. So I'm going to add another dimension, which is also going to be perpendicular to these dimensions. But since it's already, I've already stretched 2D into 3D, and if I had actually a 3D graph, I couldn't really put another perpendicular dimension in there. So for the sake of convenience, I'm going to put it in right here. But I'm going to make it a dotted line so that it looks kind of like a reflection, almost as if it's on the same angle as scale, but not the same thing as scale. It shouldn't be confused with scale. Although it probably does get this dimension of scale. Well, no, it definitely does get this dimension of scale from our actual scale axis. Anyway, let's go ahead and just dot that line. So now we have a fourth axis. And once again, you're saying, that's great, Dustin, but what is this axis? Spit it out. So this axis, the real part, is going to be, well, it's going to be the universe, or the observed part of the observed part of this universe. And then the other side is going to be the observer. U for universe, universal frame, frame of observation if you're working at a smaller scale than the universe. And I, just because I observe. It just makes sense to me. So we have I for the observer. And so now we have this fourth dimension of observer observed. And it's a dimension that we use every day. We gauge everything from its relationship to us. How far away the camera is, how far away work is, and how far away the closest grocery store. You know, you cannot observe reality without the observer-observed relationship. Now you can have like this kind of like balanced state right in between observer and observed, and that might really work in a good Buddhist sense if you're into meditation. But you know, more than that, it's adding, you know, first we had like this two-dimensional, you know, look at reality, you know, with this extra dimension of scale. Well, now we have three, you know, let's say you're looking at like a map or you're looking at a graph, and that's kind of like the funny thing about like all graphs or, you know, visual representation sense. Oh gosh, I wish I could remember his name. The guy who invented the idea of the infinite vanishing point of perspective. Berlucci, something close to that. Bertolli? No, that's pasta. Or anyway, that guy, you know, had this idea of the infinite vanishing point, and you draw, you know, everything in the picture tends towards, you know, that vanishing point. So if you have a house, you know, that line goes this way, this way, this way, you know, and then the parallel lines stay parallel while everything goes towards, you know, this infinite vanishing point. Okay, a box here, so that. Yeah, so your parallel lines stay parallel, and your lines extending in the axis towards the infinite horizon point in that direction. Sorry, that was a bit of an aside, but I think it's really cool. You know, if this is basically, you know, smuggled in infinity, just like this guy, and everything retreats to that point, just kind of like everything kind of retreats to this point. But also the thing to keep in mind is it's advancing away from the observer. You know, and by, you know, putting the role of the observer in, you complete the picture. You create a 3D perspective. And we see that with like a lot of graphs, like, you know, like this, you know, basically like anything that requires a perspective of, you know, a two-dimensional object, by having an observer, that adds another dimension, 3 dimensions. So this board is 2-dimensional, but me in relationship to this board is now 3-dimensional. And that's how this observer-observed relationship always works. And beyond that, it is also a way to cut up, you know, divide, characterize, categorize the universe. There is me, or the, you know, your observer or your detection equipment, you know, whatever it is, you know, and then there's what it's detecting. However, in the case of like everything, right? You know, this is the entire universe. And for the sake of argument, you know, let's say that the entire universe is represented by 10 bricks, just regular, doesn't matter what kind of bricks, but let's just say 10 bricks. But to have an observer, you know, each one of those bricks can represent anything you want. You know, it could represent 1 billion galaxies, whatever. But one of those bricks has to represent the observer. So if you have 10 of the bricks and one of them is the observer, then the observer's relationship is 1 to 10, or, you know, if you subtract the 1, then, you know, it's 1 to 9. But yet there's always this idea of inverting the whole to make the part. Just like if we were looking at how long it takes, the Earth to travel around the sun, we could measure that distance, or time, basically any number of ways. Um, I'm sure you all know that you could record it in days, and you would have 365.25. As the whole rotation of the Earth can be divided in, that many times, and you would have one day equaling one of those measurements. If you were instead measuring by seasons, you would measure that 4 of those seasons passed, and any one season would be one of 4, and so on and so on. But basically, you can see this inverting the whole to the part, the observer, the observed, and you can't get away from it. Now, most of the time we don't need to think about it. It's just so built into the way we look at the universe. It's just natural and a matter of fact. Same thing with scale, really. So, I mean, even though I said putting scale in was kind of cheating since it was already there, but it was already there. It's already a part of everything, and it is a dimension of physical space in a way that's almost more real than this one of observer and observed, because when we typically look at this idea of depth of space, or volume, this kind of like area of space, then what am I trying to say here? Sorry, I lost my train of thought. But yeah, so scale. We typically describe everything in space in the 3 coordinates of x, y, and z, but you really need 4, because without 4 coordinates, well, okay, so you can make x, instead of having 1, 2, 3, 4, 5, you could divide 1, 2, into 0.51, 1.52, or keep dividing it further and further so you can have smaller and smaller scale. Or if you're working with really big things, you could like make the numbers bigger and bigger to fit within the same scale. But if you wanted to represent everything in the universe, you would, mathematically, or at least, in this sense of mathematically, you would need a graph or a map the size of the universe to represent the universe, at least is in a certain level of detail. So it's not just that X, Y, and Z, get smaller or bigger. They get smaller and bigger by this guy here, scale. Scale is a dimension of space. Depth is a dimension of three-dimensional space. And we kind of know that every time we, get into the ocean or send rockets out into space. There is, scale. Anyway, we're used to working with it, I guess is my point. It just makes sense. We don't really think about it, in the idea of X, Y, and Z. But just how if you had a three-dimensional graph with X, Y, and Z, but you're only using 2 of those, like you're only using two-dimensional, like a two-dimensional type analysis or problem or whatever, you wouldn't use the Z-axis. Like if you're just writing 2 coordinates, then, it doesn't matter what your third Z coordinate is because you're not using it. But that doesn't mean the third coordinate goes away. It just means it's not being used. And it's kind of the same way when we, treat scale, not as its own dimension. It's always there. Just because we don't use it doesn't mean it's not having an effect, doesn't mean it's not part of the actual structure. Just like Z is still part of the X, Y, Z structure, even if only 2 coordinates are used. But on those lines, literally, I guess, we can now, we now have a real and maybe then some depiction of what we consider physical space, 3 dimensions, and time, or 8 dimensions really, or 4 dualities. So we kind of have everything here, but then like, okay, that's a neat graph, Dustin, but that doesn't mean it really represents reality. Except for I think it kind of does, and that might be the craziest part about this, because just like the whole thing, whatever axis you use, has to be included in the calculation. So Uh, this part's a bit tricky. Sorry, let me think here how to explain it. So the space, if you know anything used within this kind of rubric, this rubric, space has to be a dimension if it's used, tautologically, and they all have to be within space. And I strongly believe that this whole setup here is why we have three nominally or more dimensions of space, even if the more dimensions are ones we're already used to using. But we now have four axes plus scale, of these dualities that compose everything. And this starts to get us a lot closer to being something useful, and like why you would gonna spend an hour or so of time listening to some crazy guy on a very badly produced video talk about reality. Um, so kind of at this point here was where my mind was blown a bit, and I didn't quite get to it by this route. It was entirely like a kind of like a back way, and I trying to figure out what I was working with, groping blindly in the dark, until I realized this was a lot better explanation of the concept I was working with. Sorry if I'm looking at the board all the time and not the camera, but that's what kind of video this is going to be. So yeah, here's the universe. But then you're probably also saying that there's some pretty big things I haven't covered yet, like gravity. Like, well, you name a lot of things I suppose I haven't covered yet that are really important to physics, and but gravity would definitely be at the top of that list. And I'm going to get there very shortly, I promise. But before I do, I kind of want to talk about. Remember, I was saying earlier, dimensions are both measurements of themselves, composed of smaller dimensions, or not smaller, or separate, you know, conjoined dimensions. So if things are composed of joined dimensions, then they can also compose joined dimensions. Um, and I think this, I don't know if there's anything more fundamental you could add to this setup here, but in a less sort of a more of an implied sense rather than a fundamental sense, we can start looking at how some of these axes play together. So, you know, first off, since we already kind of see how scale gave its dimensionality of C to everything, or at least C as far as we currently understand it to everything, and then space also gives its dimensionality to everything. So we have three-dimensional space. Time gives its dimensionality to everything because everything exists in time. Existing is almost synonymous with time. Um, if there's no time to be, you can't be. Uh, but we also have these. Let's see here. Okay. Let's use orange for this guy. I think I was looking for. Oh, there it is. I was looking for purple because this line is blue. I don't know. It does not like it matter. But we can draw an axis between them. And this axis is going to be composed of space and scale. So how do scale and space relate to each other? What is the scale of space? And I strongly believe that scale is pi. It's the ratio of if two dimensions compared to the radius of a circle compared to its circumference, yada yada. But you have to use pi to determine an object's spatial transition. So pi appears to be the scale of space, but also, let's see here, of time. You can see, just like everything is reflected across the line, where space is kind of reflected across that zero line by time, mass is reflected across that zero line by energy. This scale and space uh, I forgot the word for it, geometric algebra, two axes. Anyway, these two guys uh, combine to each other and reflect in an equal combination of scale and time. So you get pi on this side. And so the scale of space appears to be time, uh, appears to be pi. uh, all right, so that's interesting. Um, but unlike, scale goes from 0 to infinity, or as far as you care to count, um, as does space. Pi doesn't extend necessarily between 0 and infinity. It extends between, this axis and this one. But since these axes also extend to 0, from, towards 0, towards infinity, then so does this one. So in a sense, this one is also extending, like this, but at an angle, if that makes any sense. Hopefully it does. All right. But we also need to talk about how scale relates to mass and energy. Now, independently, on each axis, we know that we have the scale of c, um, but that's like, we call it the speed of light, or, the speed of causality, the speed of information transfer, the speed of gravitational waves, which actually that's kind of like what one of the things that got me down this rabbit hole was like, well, why is the speed of light the same as the speed of gravity? Like, why don't we call it the speed of gravity? Or if it's not the speed of light, then what is it? Um, that was kind of like a long route how I got here. But if we talk about, how scale relates to mass, it appears to relate by the fine structure constant. Same thing with energy and scale. Again, this bi-axis, coaxial, no, anyway, bivector. This bivector is reflected across the 0 line with alpha on each side, just a reflection of it. This isn't the same thing as this, but they are in a sense the same thing because they're part of this duality, or maybe even quadrality might be a better term, but doesn't really matter. The idea is that it's dual. It's, equally reflected across that 0 line. So now we have the scale of mass and energy, how mass and energy kind of order themselves. So we see in energy, that's how we first came across the fine structure constant was, that division between, was it the hydrogen lines? Don't quote me on that. But, there's this really tiny division, that appears to relate at about a scale of 1 to 137 of the, it's just a ratio, just like this is a ratio and this is a ratio. Now, since it's across this 0 line, I'm pretty sure that instead of it being 1 over 137, then it should probably be 137 over 1. So maybe you could call that the gross structure constant and the fine structure constant. But really, it doesn't really matter. It's just the idea is that, this duality is being reflected, both in the universe and, how we're looking at it here. So now we have scale interacting with all these guys. Our other two axes composed of a real and imaginary part. So, and this would be the imaginary side of this. Well, now we have a trivector, on each side if you look at each, the way things are here. And then especially if we kind of, remember I said this observer-observed relationship is, this is actually a reflection. If you put the observed portion over here on this side, then you kind of get your picture of what we see when we look out into the universe. If instead you flip the axis this way, then you're looking inward, except for you got to flip scale too, I think. But so in a sense, we can kind of see you know, this imaginary side representing like all of the imaginary, the unobserved, that might be a better term than imaginary because obviously energy and time are real. Um, so the unobserved and the observed portion, and it really starts to look like like let's say you go this way, and you have alpha, ordering energy by scale, and keep in mind that this scale is negative here. So even though these two sides like look equal, this is like equally small compared to an equally amount of big. So in some ways, this gets smaller and smaller as it goes this way. This gets larger and larger, and we see that with divisions of mass or energy. Yeah. So if you flip the axis there, and you can look at kind of like smaller and smaller extensions, and it starts to look a lot like, I'm just going to draw, like, imagine like this is a pyramid here. It really starts to look like this guy leads into, well, let's do a slightly different color. I don't know why. Leads into this is kind of hard to draw. I don't know, but and it's almost like these axes flip, I think, as they cross each division of order under alpha. So like maybe space and time kind of flip sides. That seems to make sense to me, but that's nothing I can even remotely prove or say with any degree of confidence. But regardless, you look out and you see things getting bigger and bigger, or at least bigger and bigger in like kind of like a real sense. Of course we look out and we actually see things getting smaller and smaller because they're getting farther and farther away, which again does tie into this whole dynamic here. But in like this idea of like a real sense, like how much mass these things have, that might be a better idea of massiveness. We see increasing orders of massiveness. First there's us, then there's our environment, then we look out farther and we see our world, our solar system, our galaxy, our local cluster, and then we also, of course, when we see those things, we see them in connection to other things of that scale. And everything at scale appears to play together, as well as play with things that are smaller scale still get to join the party, because they all kind of, the things that are smaller scale are all adding to this in their own small way. And we also see the same thing on the other side. So we have the other side going the other way. This is our zero line. So we have a pyramid here, and then you have smaller and smaller and smaller. So you have, us, you know, the Democritean, the atom in the sense of the Democritus kind of word. And then you have, the, I don't know, quarks, gluons, etc., getting smaller and smaller down. And again, like, I don't think we're never going to find a fundamental particle like, the monad. It's just going to be this structure repeating itself just like this structure repeats. And we can kind of see that, right? You look at the solar system and it looks a lot like the Bohr model of an atom. You have the nucleus of the sun with electron-like planets whirling around it. It's just it's a lot bigger scale, both of mass, you know of stuffness, but also of time. Like if you fast forwarded time, then the Earth would look like just like a blur, like a ring, around a ring of potentiality or possibility, around the sun. I don't think I'm the first person to observe this before, but I also think it's really interesting, if you compare, like, say, this, stars to atoms. Well, then at a certain point, you get stars that are so massive that they can't interact with this stuff within the same causality at scale. You got to kind of like stuff it in to kind of stop it from breaking everything else because it's so massive. And you see where I'm going with this? It seems a lot like black holes. Like, well, of course, I'm already talking about black holes. But so, what is the black hole equivalent of an atom? I would looks a lot like, iron, Fe26. The point at which you can no longer, gain energy by combining things. You can only split it apart. You know, who knows? Maybe we can split black holes. Maybe we can fuse stars. It's an interesting thing to think about, at least. Good science fiction setup. But all right, so here's like this whole thing of order. Now I'm going to erase all of this stuff here. I'm going to talk about this relationship here really quickly. It's not really that important, I think, to this what I'm really trying to say. But I'm almost absolutely certain it's correct. It's one of those things I just can't shake, which means either I'm crazy. Well, it's not really an either or proposition, I suppose. Or there's something there. And so we talk about that relationship of, we could use any kind of those, characteristics we want to use, those axes. But let's just talk about mass. They'll all work together the same way. But if you talk about the mass of the observer, mass of I, compared to the mass of the observed, or the mass of the universe, that is the same relationship, because alpha kind of, at least from this perspective, the fine structure constant is going to stay the same, in whichever way you look. And it's going to order things the same way. So you have the mass of the universe is equal to, the mass of is equal to the mass of the universe compared to the mass of the universe of a larger frame. So mass of the universe n plus 1. Oh, wait. Why am I messing this up? I've gone over this in my head 100 times by now. Let's see if I can just do the other side real quick, if it'll make sense. Sorry about that. Please bear with me. So, we also have the mass of the Democritean atom. I'm not certain enough about any of this to say that it's the mass of an actual atom of any sort. But the mass of a Democritean type fundamental component of stuff is the relationship of the mass to the observer. Like I said, these keep going up. So MUN, maybe that's where I'm going wrong here. MUN, which is going to be, and then MUN to MUN plus 1. And then kind of like the same thing on this other side. M atom n plus 1 over m atom n. So there's almost this fractal order of everything, just kind of getting bigger and smaller. In this case mass, but it could just as well be space or time. So I'm pretty sure that's right and important. Okay, so it's just like I said, it's fractal. Kind of like, either which way you go, the relationship stays the same on a certain pattern, but the scale changes and repeats itself, but it repeats itself within the structure so that the whole structure works together. And I will also bet another $100 on that. To whom? I don't know. Okay. So the next thing I want to talk about is like, okay, so you have that whole graph, and all right, so you have these, this relationship of things, like that's interesting, but, is it altogether, like, is it useful? Like what are you explaining here really that's new that I'm going to get out of this? Well, I think this one right here is important. So remember those bivector axes, things combining, together. So let's combine two of them together. Let's use time, and then let's use the observer. And then, as we all know, one thing we know about time is it goes on. So, it increases. So as the time of the observer increases, then the opposite side of this axis, the universal frame, that decreases. And you know what? Sorry, I completely misspoke. I'm sure that's correct too. We'll get to it. But no, I'm sorry. Time of the observer increases. The time of the observed or the universe decreases. Dropped it again. So the time, and that seems kind of weird, right? Like our time's going forward, but the universe's time is going backwards. I mean, yeah, kind of. Not exactly. It's just that, like, think of this like an hourglass. Like all the time in the universe is held by the universe, and the universe gives up its time so that all the things in the universe can have time. Or the sands, as our time goes up, the sands of the hourglass run out. You can also look at, this as entropy, going from a high level of entropy to a low level of entropy. But again, these axes are opposite each other on this mirror. And so just like, if you walk away from, your mirror reflection, then your mirror reflection walks away from you. So as the time, in space and time, we're on opposite sides, right? So as the time of the universe decreases, runs out, is used up by the universe, however you want to look at it, then the space of the universe, or the observed, has to increase. And then that we know as cosmic inflation. The universe is expanding. The universe is getting larger. There's more and more space every second. 76 kilometers per megaparsec, thereabouts. So this is your source of dark energy. It's that energy is coming from the time that the universe is giving up. These two are across the axis from each other, part of the same thing, the same space-time. It's just keeping space-time balanced, because everything has to stay in balance, because everything has to work together. There's no other choice. You couldn't break that law if you wanted to. You can change your perspective on it, but you can't break it. And then, lastly, if the space of the universe is increasing, remember the other side of that is the space of the observer, and that decreases. The space of the observer decreases, and we call that gravity. In one sense, it's our own space. That's what keeps, like an object like the sun, or like you and I, together is our personal gravity. That's how we always stay together. Our space is contracting every additional increment of time of observation. We stay whole. But also, remember, we're all part of the greater universe. So in a sense, me, you, and the sun, we're all part of the same solar system. So in the solar system is still part of the universe. So, that space also decreases. And you can calculate that by, the mass of one object times the mass of another object over the distance between them, times g. And, g, if you've looked into Dirac's theory of large numbers, really appears to be, very roughly speaking, 1 over the entire space of the universe, or 6.21. I should have looked that up beforehand, because I always get mixed up with Avogadro's number. 6.27 times 10 to the negative 21. That's probably Avogadro. But you know what I mean. The universal constant of gravity appears to be one component relating to, this whole, 1 over the mass of the universe, mass of the observer, mass of the observer is equal to 1 over the mass of the observed. Time of the observer is equal to 1 over the time of the universe, the frame of observation. And the space of the observer is equal to 1 over the space of the universe. 6 point whatever times 10 to the whatever. Small number, but because everything's just being divided by 1. So now we've finally talked about gravity. We've talked about dark energy. And also on that subject of dark energy, back on the graph there, the big old drawing thing. We talked about how the scale of space is pi. So the relationship of space to itself is pi. And that relationship changes over, over the age of the universe. And that does also seem to roughly equal 76 kilometers per megaparsec, or something close to that amount anyway. So if this is correct, then not only do we have a reason for expansion and gravity and dark energy, and like the rough approximations for it, very much relating, to the idea of Mach's bucket. Thanks to Dr. Unziker for that whole thing. I was really trying to figure that one out. That also helped lead me here. And so yeah, we have some pretty interesting fundamental relationships explained, hopefully in a way that makes sense. Hopefully I don't seem like a raving lunatic. But if I do, I apologize. So what else can we talk about? Obviously, I guess there's more. I guess, it's that whole observation thing, right? Like what's going on with the observer-observed relationship. We see it in the Heisenberg uncertainty principle and a lot of aspects of quantum mechanics. To the point that we get this idea of the wave collapse. Your various interpretations of quantum mechanics. What is what determines what an electron is, or what determines what a hydrogen atom is. And it really seems to be determined, from the way I look at it, by the observer. In a very real way, the mass of the observer, or the space, because all of those things work together. So wherever you plug a coordinate in, you have the equal coordinates everywhere else. So it doesn't actually really matter, it's not like it's just mass that determines everything else, or it's not just space that determines everything else. But if you have a coordinate, within that, reference system, that shows you where the mass is, it also shows you where everything else is. Just, you cannot help but be situated, by that. So, and then you have that observer, or let's keep it the same direction. Observer or observed and observer. I'm sure this video is getting too long. I'm getting tongue-tied. So you have the observer-observed relationship, the 365 or whatever it is compared to the 1. But so you plug this in, and tongue-tied for heck. So, the observer's relationship to the observed, determines the observed. And we see that in relativity. So, where am I going with this? Just basically, just by the act of observation, and there's the whole thing of, so what do we use to observe, the universe with? We use, generally speaking, we use light. We see things. We can observe with our ears, and that would be like a different speed. But in terms of like how we define the, the universe and things like that, we typically use this reference point of, visual observation using light. Um, and of course then there's entanglement. So it's like your mass, because this is all going to be about you, right? Because everything that you've observed has been through your frame of reference. So your mass is going to determine like how everything works according to you, including, this massless particle of the photon. And then that massless particle is going to, basically by this now moment, when you divide the entire universe into like this 1 over time of the universe, which I don't know if I mentioned that or not yet, but t now is equal to t time of the observer is equal to 1 over the time of the observed, or the age of the universe. So basically, all of the time, in the universe is composed by all of the, and it works both ways, by all of the added moments of the time of the observer. And of course, that necessarily means that in the early universe, as we would see it, that, this number would be a lot bigger, because, as the age of the universe goes on, as we see it, there's more time. So like 1 over a bigger number, meaning time is smaller and faster. So if you feel like time is getting faster the older you get, it's actually for a very good reason. And I also strongly suspect that this relationship, in combination with the other factors it has to balance, really is, explains the initial expansion of the universe after the Big Bang, the very rapid expansion that eventually gets smaller. Time was a lot bigger back then, and bigger in the sense of time means slower. And so, yeah, that seems important. But then also, I guess kind of like, anyway, so before I move on, I really think this determines, this t now determines the state of everything, because you can't get smaller than this, right? This is the defining moment of time in any given, instance. And so from that perspective, it's always going to define this, if you're looking at the smallest possible aspect of something, it's going to define what the, speed and mass and time and all that of what's observed, and that is, I wouldn't say the collapse of the waveform, but the determination of, at the lowest fundamental level, through the entanglement of observation with the fundamental, just the same way we divided the universe into all the various axes, you also have all of the same components, hence universality. Yeah, so all that stuff works together. And so now we've talked about, in a very loose way, the measurement problem. We've talked about dark energy. We've talked about gravity. The only thing we haven't really discussed yet, and I'm not sure I need the whiteboard for this, is dark matter. And this is kind of, since this is what, really got me into this whole subject, what is dark matter? I don't, and I think the evidence is, more and more starting to point in the direction that there is no dark matter. We don't know what it is anyway. We have some guesses, but then at the same time, dark matter explains a lot of stuff. Well, what if, instead of there being dark matter, there is dark space? So, if you look at our original graph, just really quickly. So, this side is energy, this side is mass. Energy has space that we call the electromagnetic field. Mass has space that we call space. Mass is just, or space is just the mass field. and it resolves through time the same way the electromagnetic field does. Remember I was talking about the whole, like, how I got into looking at it, like, is gravity left-handed or right-handed, and like, oh, maybe the hands fit together, and like, well, of course they fit together because they're the same darn thing, um, just at a different scale. Um, but then also possibly flipped, right? Because there's this zero line here across. So in one sense, the magnetic field is the same thing as space. But then in another sense, it's flipped, right? So, uh, and if space is to mass as the magnetic field is to the electron, magnetic fields have density, flux lines and whatnot. Uh, Space also has density, which is kind of a fancy way of saying, forgive the wrong color, what if galaxies are just bigger on the inside? Because they have denser space fields. You know, the whole, pi affecting, how much space is in a volume with a given mass. And a lot of mass is going to have, that number is going to be crunched down like really small. So from our perspective, it looks like a small amount of space inside the galaxy. But from the galaxy's perspective, I suppose we, I don't know. That's too hard to think about. Um, but, but yeah, galaxies are bigger on the inside. And if galaxies are bigger on the inside, if there's more space in there than we're giving it credit for, then objects within the center of the galaxy are going to be moving faster than what we determine they are. When it's going to make the things on the outside, where space is less dense, look like they're moving faster in relation to the stuff on the inside. So fast, in fact, it looks like they might fling themselves out into the interstellar medium, but they don't. And we theorize that's because of the dark matter halo, but in reality, it's that's a rather bold claim, but of course I still think I'm right, but we'll see. But in reality, uh, yeah, it's just, you know, they're all moving roughly at equilibrium. Once you account, the different amount of space in there, and if they're moving at equilibrium, you don't need dark matter. You just need dark space on the inside instead of dark matter on the outside. Um, it's a hard thing to think about, like, what does more space look like? And I think it's just more compressed. It's the same amount of stuff squeezed in. It's just, and we see that, like, in a certain sense in like planets, right? Or stars, the stuff in the middle of the star is more dense, from the compactification of gravity. Um, and I think one thing I totally skipped over is that the idea of gravity and space essentially being the same thing. Um, and it makes sense to me. I'm not sure why I can't find, like, I searched YouTube, like, gravity is space or space is gravity. I couldn't find anything. Maybe it was the algorithm, maybe it's my horrible search skills, but it just seems so obvious to me. If we're connected to everything in the universe through gravity, no matter how far away a star is, it still has some gravitational pull on you. And we're connected to everything in the universe through space. Gravity and space are just the same thing, and it's additive, just like the magnetic field is, right? Like, if you have a space between one object and another object, it's like a string of space connecting them, or a string of, or backwards time separating them, depending on how you look at it, or, time running out, separating them, or space. Anyway, it gets confusing, I apologize. Um, but then if you have another mass inside, they also have a string connecting them, but they're inside of already a given amount of space. So instead of simply connecting it, it's like a string would. If you add like an extra length to a given length of string, it's going to make your string sag. Not the greatest analogy, because I suppose there's some gravity down here pulling on the string, but we do the same thing with the whole rubber sheet analogy too, so we're used to it. But yeah, instead of warping space, mass, in a sense, creates space, in the same way that, at least, in a manner of speaking, the electron, or the movement of the electron, through space and time creates the magnetic field. The movement of mass through space and time creates the mass field, or space, or gravity, or whatever you want to call it. And so, and it works the same way as under Einstein's, field equation. I've tried doing the equation to see if I could kind of like make things match up a little bit. It's still beyond me. I do plan on taking a few courses on linear algebra, geometric algebra, and quaternions, because I don't know if you looked at that, at this guy right here, there really does seem to be a whole quaternion type thing to it, in the same way that Hamilton, came up with like this idea of rotating a three-dimensional object by adding a fourth dimension. I, J, K, whatever anyway. So, yeah, I don't know what else I can say at this point. I've kind of gone over everything I want to say, and I'm sure this video is way long enough already. If I've forgotten something, I'll come back. If you have any questions or comments, I would greatly appreciate them. So please hit me up with those. And I'm gonna put my hat out. And if you found this video interesting, you want to donate, feel free. I've poured a lot of obsession, at least, in time over the last couple of years into this. So if you want to help me further my education by getting some linear algebra and geometric algebra under my belt, which I think is needed to fully explain this in a more scientifically robust way, I'd greatly appreciate it. Other than that, see you guys next time. Thanks a lot.